Hello student, welcome back to pre-video of ATC on topic 3 equivalent representation. In the last pre-video we have seen how to write a regular expressions by some of the regular language using a statement, then using those statement over the alphabet you can able to write a regular expression. We have seen plenty of examples. Let us see, we see some of the complicated examples in a classroom on board. Then today we'll be discussing on 3 equivalent representation. We have seen this kind of in a different format. It is a circular format. If you have a regular expressions, then you can able to construct the finite automata. If you have a finite automata, you can able to construct the regular expression. So then if you have a regular expression, you can find out the regular language, you can have a finite automata. If you have a regular language, you can construct, or you can have this one. So this cycle will always be there. So always you have to give a input regular expression which define the pattern. And let us see in this class, they will give the regular expressions. How do you construct the corresponding finite state machine? Will you do it as you have as your own method? No. So one of the approach as introduced in the finite state machine, that is Kleen's theorem. Kleen's is a scientist. His theorem is given as, that is the reason is this theorem is called as a Kleen's theorem. His statement is every regular expression, there is a deterministic finite state machine. Then that is a deterministic finite state machine or finite state automata that defines the same language and vice versa. So every regular expression, there is a DFSM that defines the same language and vice versa. Every DFA, there will be equivalent regular expressions. So how do you construct this? Look at this. Kleen's theorems. So I have given some of the assumption. We'll see how to do that. So statement is will be like this. If the language is generated by regular expression is a subset of or equivalent of language recognized by finite state machine. Whatever the language is generated by regular expression, which is also recognized by finite state machine. Second statement will show that language generated by regular expression is a subset of language recognized by finite state machine and vice versa. Language generated by regular expression is a language recognized by finite state machine is a subset of language generated by regular expressions. So whatever the statement you have seen in the previous slide, how do you prove them? The part 1 is, for any regular expressions there will be R. The language L of R is recognized by finite state automata. R is a regular language. So we can also prove by induction on the size of R. So that is nothing but language generated by regular expression is a subset of language recognized by finite state machine. Then we'll see the proof. Kleen's theorem is, that means if there is every regular expression, there is an equivalent deterministic finite state automata. Right? So statement is there, any regular language can be recognized, can be accepted by finite automata. So that is a statement. Procedure is, any language that can be defined with a regular expression can be accepted by finite state machine and so is regular. That is what you want to prove it. The proof is step 1. We have to follow the two steps. One is basis rule, other one is induction step. For that you have to recall the recursive definition of regular expression. There are two types of regular expression. The first regular expression, there is no operators are involved in it, that is basis. Where there is a regular expression have a operator, there are three operators will be there, plus, dot and closure, clean closure, star. So first you will see the basis. The first definition of this, pi is a RE. Obviously, as a definition of RE is false good. There is no operator. So what is the state diagram of finite state automata? So there is no transition. It not move it. It is a start and there is no end at all. And second one, epsilon is RE as per the definition of RE. So there is a transition, okay, start and end with the same state. There is an empty set, and A is a RE, definitely have a transition. So there is transition from one state to other state. So thus two state is required. So all these three definition, there is a zero operators. So figure 1, 2, 3 are corresponding to regular expression phi, epsilon and A containing a zero operators. As I explained, so it is a zero operators. Let us move to the step 2. We'll go by induction step. Here the operators are involved. What are those operators? We'll take the case number 1. If R1 and R2 are regular expression, then RE is equal to R1 plus R2 is also a regular expression. So then how do you construct this? It is a union. Similarly, it is a union. So how do you construct? First you have to take down the machine. What is that? Let M1 is equal to Q1 sigma Q1 and F1 delta 1 be a machine which accept L of R1 as a language corresponding to regular expression R1. Then similarly there are two machines, right? The union is that R is equal to R1 plus R2 is also a regular expression. Whenever R1 and R2 is a regular expression, R is also a regular expression. So this is one is accepted. This regular expression accepted by second machine. That is plus it is indicate is union. Either accept R1 or R2. So that is the reason I have defined two machine. So that is M1 and M2. So M2 is one similarly which accept the L of R2 as a corresponding regular expression R2. Then how do you write this? Therefore, the combined machine that means M either accept L of R1 or L of R2 shown below. How do you represent? There is obviously there is a Q1 is there. There is a Q1. I have taken this is the initial state. Then F1 is there. This is the final state for machine 1. So machine 1. Okay. Machine 1. Similarly, this is a machine 1. Right. So we have machine 1 is L of R1. Similarly, machine 2, the Q2 is the initial state and F2 is the final state. So this is machine 2. How do you? So for this statement, either accept L of R1. This is L of R1. Are you agree with this? This is L of R2. Are you agree with this? Either accept L of R1 or L of R2. For that require two more state, that is initial state and final state. So F1 and F2 because after joining this two state F1 and F1 and F2 become intermediate state, then this will be the final state. This is become initial state. Let us see how this transition is happening. Okay, I have taken the Q naught as the initial state and Q. Okay, I am joining those by epsilon, right? You know what is epsilon is doing us, right? QF. So now I am joining that. So I am also joining F2 on that. Then F1 and F2 become intermediate state. This way you can construct. So for union operators, this is the case number 1. So construction of combined machine, is it accepting? Because all the set of Q M1 machine and union with the M2, and I am taking a 2 additional state Q0 and QF. This will be the Q of combined machine. The sigma is remains same. Q0 is the initial state, QF is the final state, and delta. Where has defined this? What is that? Then what is the delta I have to define? Delta Q0 on epsilon will give Q1 and Q2, right? Q1 and Q2. For general, delta of Q comma A, it may go to Q1 on A for Q1 minus F1. That means a intermediate state. Q2 comma A for Q2 for this one. So for this, any transition is happening, okay, for in general. So for the F1, it will go to F1, delta of F1 comma epsilon is equal to delta of F2 comma epsilon. Both will go to the QF. So this is for second one. So next, case number 2. Don't worry about this. Some animation is not supporting iOS. So I'll clear it later. So concatenation. So second case, if R is equal to R1 dot R2, where R1 and R2 are RE, then machine to accept L of R1 is shown below. The first one, right? First one, it is machine 1, L of R1 is accepting and L of R2 is ready, that is L of R2. Then how do we combine? Because it is a concatenation. L of R1 followed by L of R2. What is the operator is in between? Dot operator. How to join that? By epsilon. So then F1 become an intermediate state, F2 become final state, and Q1 become initial state. So now have to define construction of combined machine. Construction of combined machine. So here it is combined machine Q1. This is Q1 and this is Q2. These two are combined it. Sigma Q1 F2 delta. Where delta is, so as usual I have seen in the previous, we have defined this. Then this is right. Then F1 will go to the Q2. These are the transition. Third case, clean closure. Clean closure. So that is means it is rotating itself R1 star. You know what is star already. It appears 0 or more occurrence of R1. So now the machine accept L of R1 as shown below. I am taking, there is only one machine. So Q1 is the initial state. F1 is a final state. Then it is called. So for that you want to join. Because whenever it is R1 star, it may generate even epsilon also. So I am joining these two by epsilon and rotating it. So without accepting any input will join to that. So because that is the one, and it may generating n number of times, right? So that is the reason this is the transition diagram. Then what is the construction of combined machine? So there is a Q1, capital Q1 union capital Q2. Capital Q2 will not come here. So only union of Q1 and F1, right? These two are joining it. Okay. This is the M1 capital Q. Additional two state I have taken here. That is Q1 and QF. Right? Sigma Q0 is the initial state, QF is the final state, and delta. Delta will see similar delta. So Q0 on 0 will go to Q1. F1 on epsilon will go to q1 as well as f. Correct now? So in general you have to define like that. So delta of q comma a, delta 1 of q comma a for q1 belong to q1 minus f. So with that is a definition you understand. So that is a theorem. So that theorem will say what exactly that works, how can construct a regular expression in, we'll see that in a little later. That is our application of Kleen's theorem. So that means transferring a regular expression to NFA, that means they have given the regular expressions here. What is that? A bar B whole star ABB. For that you need to, this is the expression as given, we need to construct a, so construct a NFA for that. I'll take the example, our previous example, A bar B or star ABB. So for that either is accepting A or B star. I'll take first A and second B, and which is comes in a case number 1 union. So that means it is accepting A or B. The A is constructed and B is constructed. I need to construct A or B star. Now I am doing. For that I am taking two more state, 4 and that is join and 5. So I just, this is accepting A or B. A or B. Then what about star? What about star? Star, for that it is include one more, yes, right, and also will go to the one more, this one. So this is 1, this is A or B, it is a union, and star is a clean closure. So two theorems are applied. Okay, what is remaining part of this expression? ABB. So we have to use that. So 6 A B 8, which is the final state is 8, then 4 is the initial state. So this way can be transferring any regular expression into the finite state automata. So let us see one more example, regular expression to NFA epsilon. Convert A plus AB star, that means AA either B star to NFA. How do you do that? First you take the AA. I'll do that. AA. I'm joining what is the in between concatenation. I joining with this. This is a case number 2. I'm taking AA for this. This is R1 dot R2. Okay. I have taken this much. Second one, this become intermediate state. So second one, either accept A or B, right? B as constructed. So now how to join? What is the join has taken here? I have taken one more state. So that is the initial state. That becomes the initial state. So this is a way. So we have only here AA and B is over. Either accept AA or B. But what about the star? Star is remaining now. So star is remaining. You need to have one more state that you have to join. It becomes an intermediate state, then finally will be final state. So and also one more epsilon is without accepting. Suppose in this case this will become epsilon, then this is to go epsilon and this. So anything it can come. That loop has come. That is case number 3. Case number 3, clean closure. This way can be constructed. Right? So now you can see some more problem. I can take the 0 and 1. So this you have to join. This become intermediate state. Then you take 1. Then you have to join these two. Right? You have to join. Okay. So I have to use the two more initial state, then I'll use other one, okay, we'll join these two, right, go over the final state, then this will become epsilon, this will become epsilon, the followed by this one, right, this is the followed, right, followed by this. You have to construct this very easily, then you have to do this, that becomes epsilon. It is lengthiest, but I shown it in a animated way, so we have to clear this problems on board. I'll go by step, so this is very easy to understand while I will be clear it in the classroom. Okay, so these are the example I given for you. You should have to work out at home, and any one of them are not possible to construct, please let me know and I will do it in the class itself. Thank you.